Alright, so we were discussing integrals of piecewise constant functions, and we have already seen one example in which there is a function defined on some bounded interval which is piecewise constant with respect to two different partitions of the interval. And we saw that the integral of the function with respect to both the partitions is the same. And we mentioned at the time that this is in general true. So this next proposition is just about that the integral of a piecewise constant function doesn't really depend on the choice of the partition. So let's see the statement. Let I be a bounded interval and let f be a real valued function with I as its domain. Let me write at once. Let me continue the sentence and let this be a function that is piecewise constant with respect to the partitions P and P prime of I. Then the piecewise constant integral of f with respect to the partition P is the same as its piecewise constant integral with respect to the partition P prime. So the choice of the partition actually doesn't affect anything. Yes, you need a partition to really calculate the value of the integral, but that does not depend on the choice. Anyone can choose any partition. F has to be piecewise constant with respect to that partition. The value that you will get will be constant, will not change. So its proof is this exercise 3. So for the proof, we will have to wait to see how the exercise is solved. Do you remember that we defined piecewise constant integral of a piecewise constant function, and that was version 1, where we do it with respect to a partition. But now that we see that although we do have to do it with a partition, but the choice of the partition doesn't affect anything. So this knowledge allows us to next give another definition again of integral of a piecewise constant function, but now we won't be depending on the choice of the partition. So this will be version 2, and this is definition 14. And this is the definition of piecewise constant integral part 2. So the definition goes like this. Let me do it on that side. Let the beginning of course will have those ingredients. Let I be a bounded interval and let f from I into R be a piecewise constant function on I. Okay, that means it is piecewise constant on I with respect to some partition. That we are not saying. So this in fact is using the second definition of piecewise constant function itself, where in the background there is at least one partition with respect to which the function is piecewise constant, but we are not saying anything about that. Okay, it's there. The piecewise constant integral of f over I is defined as this. The notation is also like the previous one, but this time we will mention the domain of it, the interval over which we are doing integration instead of any partition. But it is defined to be equal to the PC integral of f with respect to some partition P with respect to which f is piecewise constant, where P is a partition of I such that f is piecewise constant with respect to P. At least one such P exists because we are saying that f is piecewise constant. So we have chosen any P and we have defined the integral like this. The previous proposition guarantees that this value is independent of the choice of P. If someone else chooses some other P, say P prime in place of P, f is piecewise constant with respect to that partition also, then the PC integral calculated with that partition will also give us the same value. Okay. Now if one goes back to that example where we noticed this thing for the first time, then we can write this. This is going to be example item 15. If f is the function from that example, from the previous video, then the integral, the interval over which the function was defined is the closed interval 1 comma 4. And if you remember, we calculated the value of the integral to be 10, and we used two partitions, but of course the value will remain the same. Okay, now that we have defined the PC integral of a PC function on an interval, we should next look at its properties. I mean, the properties that we are all familiar with, which we encounter in school for the first time, and we use it freely to calculate integrals. For example, if without thinking too much, let's go back to your school calculus. If say we want to integrate this, although this is something else, okay, just to make it the same as what we encountered in school, let me just take limits also. Okay, so this definite integral, what do? You of course do it in steps. In the first step, what you do, you take the integral over each of the terms in this sum. And in doing so, you use one of the properties of definite integrals, which is linearity. That integration preserves sums of functions. And then you do the integral x cubed divided by 3, 2x here, and then you put the limits, all those things. So I am talking about those properties because the class of functions we are considering now is rather restricted. We are only considering piecewise constant function, but still we have to look at the properties of integrals even in this simple case, okay, in this class itself, because those properties will then be used to further prove similar properties of integrals of other more general functions, bounded integrable functions. And this next result is just about those properties. So let's see what it has to say. This will be item number 16, laws of integration. Sorry, I wrote 12, huh? No, what the hell? It's not 12, it's 11. I hope I wrote 11 before this also. 12 is in the second volume, volume 2. Okay, so there will be a number of laws, and we start with two functions. Okay, mainly we will need two functions. So let us start like this. Let I be a bounded interval. Of course, these properties are true for any finite number of functions. But in the simplest case, there are two functions. Let f from I to R and g from I to R be piecewise constant functions. I could have written PC functions here, but it looks a little odd to use that type of abbreviations in a formal statement. Then the following are true. You may argue that while writing the notation of the integral we are writing PC, then why not here? Well, a notation is also, we have formally defined that notation, so there it's okay. So the first property is of course the one that we were discussing about here, about definite integrals, that A, we have this, the PC integral of f plus g over I is equal to the PC integral of f over I plus the PC integral of g over I. Do you notice one thing? Of course, we have to prove this. We will prove it in an exercise. But even before that, do you notice one thing? Does it even make sense to write something like this? There is nothing wrong with these quantities. F is piecewise constant, G is also piecewise constant. So it makes sense to write the piecewise constant integrals of them. There will be some real numbers and we can add them up. And then we are saying that that should be equal to the PC integral of the function f plus g over I. But what about the function f plus g? Is it also piecewise constant? If not, then this doesn't make any sense, the left hand side. But you go back to one of the results which says that if you add, subtract, multiply piecewise constant functions, even divide, take maxima, minima, you again get piecewise constant functions. So at least we can write this. It's a different matter whether this will be equal to this or not, that we will know only after proving this. But at least we can think about this. Yes, that will be piecewise constant, and so it makes sense to consider its PC integral. Alright. Then part B is multiplication by a real number. For any real number C, we have now let me write this one first. The PC integral of the function CF over I is equal to C times the PC integral of the function f over I. In order to emphasize the fact that this is one quantity, I have put it within parentheses. Here also that same thing applies. Because f is piecewise constant, C times f is also piecewise constant on I, and that's why this integral can at least be considered. It's a general advice. Okay. In mathematics, of course, if we want, we can write all these things in words as a sentence using as few mathematical symbols as possible. That can be done. However, it will be extremely long. The purpose of a notation is to compress things and hold the entire information within it. So whenever you see an equation or anything like that which uses mathematical notation, the first advice is just think of the individual components. Do not think of the equation at once. Okay. What does an equation have? An equation has two sides. Think of each side separately. See if it makes sense. If so, what does it mean exactly? And if you keep doing this for everything, You will see that many such things you will notice which otherwise are not noticeable, which are easily ignored. For example, thinking of this equation, you may immediately think that, okay, I have to prove that this side is equal to this side. But what about this side? I mean, does it even make sense? It makes sense only when the function involved is a piecewise constant function. That's not a given thing. It's only given that f is piecewise constant. It comes from another result that then Cf is also piecewise constant. So if you keep these things in mind, you will never make any mistake. Then what is the third one? The third one is subtraction. See, we have this. Simple thing. Actually, you can already see that this is a consequence of this and this. Just take C equal to -1. Then these two will imply this. So while proving this entire result, we will also accordingly say so, that part C follows from parts A and B by taking C equal to -1. That's it. Then part D. Part D imposes a condition on F if these results will remind you of similar things that you have used every time you did calculus, at least while doing integration. If your function is non-negative, a function of course need not always be non-negative. We have functions which are somewhere positive, somewhere negative, somewhere 0. But if a function never becomes negative, then its graph stays either on the x-axis or above the x-axis. And for such functions, we in fact have area under curve, all those things. And that area is your integral. That is also going to be non-negative. So this is that same thing. If f of x is non-negative. See, being piecewise constant, f can be negative. We have already seen such examples. But if it is non-negative, oh, I should write where it is non-negative, yeah. Simply writing f of x non-negative doesn't make any sense. For all x in I, then the PC integral of f over I is also a non-negative real number. And from this and this part C, you can prove this next one, E. If f of x is greater than or equal to g of x for all x belonging to I, then accordingly the PC integrals also follow such an inequality. Do you see how E is a consequence of D and C? You see, this is given to us now. So if you think of the difference function f minus g, that difference function will be non-negative everywhere on I. You then apply part D on f minus g. So the integral of f minus g should be non-negative. But the integral of f minus g by part C is the integral of f minus the integral of g. And from that you are getting this inequality. So you see that some parts immediately follow from some other parts. Next, this is a very special case, namely the simplest case where the piecewise constant function is actually constant. If there exists a real number C such that f of x is equal to C for all x in I. In other words, if f is constantly C, then also it's piecewise constant, then the PC integral of f over I is simply C times the length of the interval I. This is also very easy. What you do, you try to think of a partition of I with respect to which f is piecewise constant. Because f is constant throughout I, you can take the singleton set whose only element is I as a partition. That of course is a partition of I with respect to which f is piecewise constant. And then for that partition you calculate this PC integral. Just use the definition, you will see that the answer is this. So it's that easy. Here is another one, G. If you extend the function f by, by introducing more zero values, that does not affect the PC integral. More precisely, this is what this means. Let J be a bounded interval such that I is a subset of J. I is the domain of f and G of course also, but there is a larger bounded interval J which contains I inside of it. If capital F from J into R is the function defined by the following rule. Capital F of x is defined to be equal to small f of x if x belongs to I, and 0 if x does not belong to I. Then capital F is also a piecewise constant function, but on J, on the larger interval, which is its domain, and its PC integral over J is the same as the PC integral of small f over I. Then this is piecewise constant on J, and the PC integral of capital F over J is equal to the PC integral of small f over I. In other words, you can see what capital F is. So what we did is something like this. Let me draw a small picture. Like, say you have this. I am drawing a figure in between these statements Please don't do this in exam or anywhere else, it's only for our understanding. Your interval I is say this. To be specific, let me consider I to be a closed interval. Although it may be any type of interval, it just needs to be bounded. And in fact, to show that, let me just consider this half open interval, which is J. Okay. Now, the way we have defined capital F is that in I, capital F is nothing but small f. Outside I in J, capital F takes only 0 values. Then capital F is piecewise constant on J. You can kind of understand why. On I, it's already piecewise constant. So if you think of the graph of small f in I, then in parts it will be line segments like this. And that's what is going to happen to capital F. So within I, capital F also shows that same behavior, because within I, capital F is just small f. And outside of I, also it's constantly 0. So that is why capital F becomes piecewise constant. And you can imagine that the integral of small f, which is going to be coming from this part, areas of these rectangles with appropriate plus minus sign, everything, to this nothing is going to be contributed by what you have outside, because outside you are going to have only 0 contribution. There the function capital F is nothing but 0, and that is why the two integrals end up being the same. And there is one more. This type of rough understanding is very useful and essential, in fact. When you go through something now, you cannot, of course, expect to remember every small detail, and while thinking of something, you also cannot and should not think in terms of, say, every precise equation and everything. You should have an intuitive idea of the entire thing, somewhat vaguely like this. If you get this idea, that means yes, you have got to the root of the thing and you understand roughly what the thing means as a whole. And let us now see the final part, H. Let J, K be a partition of I. Here we are going in the opposite direction, opposite to what we did in this previous part. In the previous part, what we did, we enlarged I to a larger interval, J. This time, however, we are breaking up I into smaller subintervals, J and K. So let J and K be let this itself be a partition of I. Yeah, so if this happens, isn't it enough to write that this is a partition of I? The author has further said that where J and K are intervals, but that's already included in the definition, right? If this is a partition of I, J and K have to themselves be bounded intervals contained in I. So I am not going to write that again. Instead, let us write the conclusion. Then the functions Now, the function small f is defined on the entire I, but we can of course restrict small f to j and to k. We will get two functions, its restrictions. Then the functions, the restriction on j, of course its notation is this, and that is going to have j as its domain. Similarly, the restriction of f on k has k as its domain, both are real valued, are piecewise constant. Okay, just like the original function f, the restrictions are also piecewise constant, but of course on their respective domains. This one is piecewise constant on j, this one on k. And what about the integrals? You can kind of guess that there will be a sum of integrals, and that's true. The PC integral of our original function on I is equal to the PC integral of the restriction of f on j plus the PC integral of the restriction of f on k on the interval k. So this is that property which allows you to say do something like this. For example, you have a function here, no, f of x dx. So we are going back to school calculus. Say the limits of integration of this definite integral are 1 and 3. The lower limit is 1 and the upper limit is 3. You often do this type of thing. You did it. And then you calculated the individual integrals. Although at that time we did not really change the notation. I mean, here also we write f, here also we write f. There is nothing wrong with that, but here we are being more rigorous. Here we recognize the fact that since we are concentrating our attention on j, on the interval 1, 2 instead of on the full interval 1, 3, so we are using the notation for the restriction function. If you want, here also you can write simply f, because the rules for the two functions f and f bar j are the same on j. Okay, so with that, this statement is over, and its proof is exercise 4. And that just completes the section. In the next section, actually we will start really looking at the notion of integrability. Let me just have a brief discussion about that. You have noticed one thing, that in spite of doing so many, I mean at least going through so many things about the class of piecewise constant functions, we did not really think about whether a piecewise constant function is integrable or not. Yes, it always is. Any piecewise constant function has a piecewise constant integral. So integrability is not an issue in this class of functions. That is why they are simple, and the way we calculate integral is also very simple. But when we go to a larger class, namely the class of bounded functions. We encountered this issue of integrability and lack thereof. Even when you consider bounded functions, forget about unbounded functions, okay? For reasons that will become clear later, even if you consider only bounded functions, if you choose any such function, it's not guaranteed to always have an integral, or in other words, to be integrable. It may be not integrable. That's why integrability itself is an issue, and the definition of Riemann integral that we are going to see in the next section will make this clear as to why some functions may not be integrable. There is a condition, okay, that is a part of the definition. And if one thinks of unbounded functions, well, then improper integrals and all those things come, which have not been discussed in this text. So those things they belong to higher level courses. So anyway, that's just it for tonight. Tomorrow, what do we have tomorrow? Number theory. We have already completed, I think, that section where we discussed divisibility by 9, 11, those things. So that means tomorrow we will solve exercises. So see you with that tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.